Well, so this is a work that is being done with Cesar, my PhD student, who is right here, right? And some further details are on his poster, which is right there. Okay. Before we start, I think we should celebrate the 40th anniversary of the school. It's actually a real impressive achievement. Sorry for the extra S here, it's a typo. It has nothing to do with my name, actually. And there's no supersymmetry involved. Well, sometimes there is. But, okay, so the title is F of R, Tale of Two Frames. So, besides being inspired by Dickens, so this is actually a tale of the two frames. I hope it's become clear in the next transparencies. So a brief review on F of R, what can it do, how is it done, what it shouldn't do, and a children frame that's all what it's all about. So what can it do? It can actually replicate really well the standard lambda CDM background cosmology, which is actually not such a good thing because you cannot differentiate between F of R and lambda CDM as long as the background is concerned. So we should look for different approaches to that. One of them is growth of perturbations, but that's another seminar. How is it done? Well, we start with general relativity, and then the Lagrangian should be a linear function of the Ricci scalar, and then the standard procedure give us Einstein's equation. And let me point out there is no matter here. There won't be any matter Lagrangian whatsoever for the whole seminar. So the right-hand side is 0, and if you take the trace, you get an identity for algebraic equation for the Ricci scalar. If there were a matter here, then on the right-hand side there would be the trace of the T mu, and this would be an identity. So you would identify the Ricci scalar with the energy density of the matter, right? So in F of R, we actually write a general function over here, an F of R, obviously, and then the equation gets a little bit more complicated than the previous one. And let me just remind you that F sub R is the first derivative. In GR, it's plane R, so this is 1. So, of course, we recover the previous case, right? And so if you take the trace, you got a little more complicated expression for the Ricci scalar. On the right-hand side, there will be T, the trace of T mu. And this is not an algebraic equation. This is a differential equation, right? So R does not equal rho or T. Does not necessarily equals T. Right? So this is going to be one of the main equations for the rest of the talk. So let me just remind you or present you, for those who don't know, the stability conditions that are really well stated in this paper by Pogosyan and Silvestri. So the standard argument goes like this. If you want some deviation from GR, so we write it as either epsilon times delta of R. Epsilon would be just a magnitude for this deformation of GR. So the stability conditions are like this. So we would like to have GR at early times. So we'd like this perturbation over here to be smaller than R when R goes to infinity in the early universe. That's what we expect, right? We'd like to have the first derivative to be of F to be positive. Actually, it comes because when we write the modified Einstein's equation, we can divide by F sub R, and then negative F sub R would implicate negative effective Newton's constant. We want gravity to be attractive, so we want the first derivative to be positive. And there is another constraint, which I'm going to talk about later on. The second derivative should be positive, otherwise we would have negative squared mass. Yes?
So in the first spectrum, you have in mind F of R as something like explain dark energy.
That's true, yes.
But coming from quantum gravity, I think you'd actually expect that as R goes to 0.
Absolutely, yes, absolutely. That's what I was going to say. I have some concerns about all three constraints over here. So the first one, as you point out, there is no need for R to be large in the early universe, right? Because it doesn't follow the trace of T mu. So it doesn't have to be large in the early universe. And if you want, for instance, this f of R to generate inflation, so we do want this to be important in the early universe, right? And something else that one has to be in mind is that only because the perturbation is small, that doesn't mean that the solution is going to be close to the original one, right? The introduction of this extra term over here introduces 2 or more orders of derivation for the metric over here. So just because the coefficient of these higher order differential terms in the differential equation are small, that doesn't mean that the solution is going to be close to the previous one, to the original one, when there is no extra terms in this equation. So I disagree with this, and I'm going to I hope I'm going to convince that this is not always necessarily true either. So that's what I told you. So the 4th order metric. And this is I told you about. Okay, so this comes from this reasoning here. I'm following this nice review by Thomas and Valerio. So if you write your f of R as R plus a perturbation, and epsilon is necessary here explicitly shown here, right? It's just a magnitude factor. And then you write that modified Einstein's equation, the trace of modified Einstein's equations in terms of R, and you expand around Minkowski, and then you end up with a differential equation for R sub 1, right? It's the perturbation around what would expect from GR, right? And then we have this mass term over here. So since epsilon can be as small as you want, the term inside the parentheses is positive, so the positivity of mass is guaranteed if the second derivative of delta, which is the same thing as the second derivative of f, should be positive, right? That's where it comes from. But please remember that that relies on making a perturbative approach to GR, right? So let's change frames, right? So I don't have time to go through all the details here, but let's make it quickly just for the sake of completeness. So if we start with an f of R, we can rewrite this expression over here with a Lagrange multiplier here. So we define this tilde phi field over here, and with this Lagrange multiplier, and then that is equivalent to require that tilde phi is equal to the Ricci scalar. And then I'm going to just rewrite f prime as chi, but just a definition. So I can write this expression over here like this, right? So this is just a replacement. Phi tilde phi is just chi r, and f is inside this potential over here, and this r is, again, f prime times r is written here. So just another different definition of variables. Then that's what we have. It looks like Brans-Dicke with this W parameter going to 0, but we do have this, which would give us experimental bounds for being larger than 50,000, but there is this extra potential term over here that makes all the difference. So now let's make this conformal transformation to Einstein's frame. That was done in Jordan's frame with the usual one where we define matter, where matter is conserved and follow geodesics. Now we're going to make this conformal transformation here, and this conformal factor is just f prime, the derivative of f with respect to r. And now we have to, just like to define another auxiliary field, this tilde chi over here, just the log of this f prime. And then when we do that, then the action is written just like Einstein's Hilbert action, so the name Einstein frame, with an extra field over here, right? To have a standard kinetic term and a standard potential term, which is defined in terms of f and f prime. Right? So this actually is really useful just to show that these f of r theories, they do have an extra degree of freedom, which is materialized here in terms of this chi field, okay? Let me just remind you, if I had matter in my theory, which I don't, but if I had, then matter would follow geodesics in the previous metric, right? The G mu without a tilde. But then there wouldn't be extra forces over here, but that's another seminar because I don't have matter in this talk. Right? So let me, in a nutshell, we start in Jordan frame with an f of r theory, and I make this change, these new definitions over here, conformal transformation, definition of tilde chi, and the potential for this tilde chi field, and then I end up with a standard Einstein-Hilbert Lagrangian with a standard kinetic term and a standard potential given by this. So the question that we posed ourselves was, well, what happens if I start in Einstein frame with a given potential, standard one, and then go back to Jordan frame? What would be the f of r that would correspond to this v over here, right? And then we realized that, so we started with chi squared, right? Just applying the easiest non-trivial potential that we can think of, right? So then we realized that it had already been done in the 1994, in this paper over here. So there is a parametric form for f and r. So in our case, n equals 2, and everything is already defined here because mu is also a function of n and the mass of the field, right? So now we can just use n equals 2 and then plug it in here and make a parametric plot of f as a function of r. Yes?
When you pass from Jordan frame to Einstein frame, you have a problem with the boundary conditions. So you have to impose for the chi.
I don't think so. There is of course, chi field should be positive because exponential of something, right? You mean chi or tilde chi? Chi. Yeah, chi, it should be positive, but I don't recall using any, I haven't checked that, but I don't think there is an issue. Because it's actually really old stuff. I'm not making anything. True, yeah, the surface, the boundary terms, the usual boundary terms, yes. Yeah, well, from the top of my mind, I'm not sure, but it's usual work, so I'm guessing that it's been taken care of. Yes, yes. I should check that, thanks. So that's the form of f, the function of r. So we can see that it's multivalued, okay? And that would be gr, the dashed line. Okay, so this red branch over here is not actually a straight line, but it's close to a straight line. So let's see what is happening to the phi field and to the Ricci scalar as time goes by. Also, let me point out that in this first branch over here, the second derivative is also positive. It's almost flat. That's going to be important later. But the second derivative is negative over here, as you can see. Right? So as time goes by, this is f a function of r. So the blue line over here is r as a function of t, and the red line is phi as a function of t. So what we have in mind is a standard inflation picture in the Einstein frame. So we start phi in slow roll conditions, right? So it will go down the potential over here. Remember that phi follows a standard phi square potential. So it goes down the hill, initially slowly, of course, but it's not shown in this plot. And then it oscillates around the bottom of its potential over here. It's a damped oscillation because the universe is expanding, right? So, and while phi is doing that, r deviates from 0, slowly deviates from 0. It's almost constant over here. And then afterwards, it oscillates also. And after 2 oscillations, it goes in phase with the phi field, right? And so this is just a blow up of this first branch over here to show that actually it's not flat. Right? You can see this k over here. It is almost flat, but it's not. Okay, so the first behavior of the Ricci scalar is around 0, but it's unstable, right? So because it goes slowly drifts away from r equals 0. So r equals 0 is not a stable solution. In spite of having the second derivative of f being positive over here, that's instability. But on the other hand, in the third branch, remember the behavior is like first branch, second branch, and third branch. The Ricci scalar oscillates around 0 in the third branch, right? So on the second hand, R equals 0 turns out to be stable on the third branch. So let's see what's happening. So we have in mind is an homogeneous universe. So that's the equation that we had, modified, the trace of the modified Einstein's equation, right? So I'll focus on homogeneous universe, as I said. And then let me just skip this for Friedmann-Robertson-Walker, homogeneous space. That equation turns out to be this one. So we have a mass term, we have a second derivative, we have a friction term with r dot squared and r dot over here, right? So let's focus on this term over here, right? The first derivative of this potential, which is this one, right? Again here. So from here, we can just integrate that. Instead of integrating in terms of r, you can integrate in terms of t, right? Because you know r as a function of t. And that's what you have. So the red line is just using slow roll, which shouldn't work, right? Except from the very beginning of the first branch, where it is actually pretty close to the one. It's amazing, interestingly enough, that the qualitative behavior is similar to the numerical one, but it's just an illustration. You follow the numerical solution, which is this blue one. So that's the potential as a function of r, right? So it's not actually multi-valued. What happens actually is that it's changing as time goes by, right? So it has a dynamical character. So what we do, before talking about this dynamical character, what we did was just derive it again, right? And then have an effective mass, which is a function of f. So we can plot it as a function of r and as a function of t as well. So the next plot has this effective mass over here as a function of t, and the second derivative of f as a function of t as well. So you compare the two criteria for stability. So this is the mass squared, right? Diverges this point and this moment and this moment as a function of time, as I said. And these 2 points correspond to those two spikes over here, right? And then, so it is negative in the beginning, and then diverges twice, and then is positive all the way from here to infinity, right? So, sorry, this is r prime over here. So it diverges when r prime goes to 0, r dot goes to 0, right? That's what's supposed to show. This is a blow up of the first branch over here to show that it's actually negative because the system is unstable, as I said, around r equals 0 in the beginning, but not in the end. And then this is, well, sorry, it's not showing up quite well. This is the second derivative of f. So it's supposed to show that it's negative over here, is positive over here, and after the second divergence, it goes positive as well, but not the same value as m squared. And this is just a blow up to show that the second derivative is positive and the mass squared is actually negative. So they disagree on the sign in the first branch. So my point is here to show that, well, okay, the second derivative is really small in the beginning of the first branch, which means that f of r is actually a really linear function of r, but that's not gr because the coefficient is 10 to minus 6. So it's actually, if you replace the gn here, then we see that the effective Newton's constant is really, really large over here. But then that's a different way to get inflation because r is really slowly changing in the beginning of the first branch. Remember, in Einstein's frame, we had the inflation, so we have the same inflationary characteristic in Jordan frame. And what happens, in spite of having a linear Lagrangian in Ricci scalar, it is a different Newton's constant. So that's why we have inflation in Jordan's frame. So that's what I just said. It still is unstable because the squared mass, it is negative, in spite of having the second derivative being positive. That's just because this is not a perturbation around GR. Right? This is not R plus a small perturbation. This is R with a really different 1 million times stronger effective Newton's constant. So that's why the standard criterion does not work here about the stability of the system, right? Okay, that's what I said. So this is f as a function of r again, and these dots over here, they point out the moments where the mass changes sign. So when the mass goes to 0. So in the first branch, almost in the for the whole first branch, this is negative, and then positive, and then negative again. And after this point over here, it oscillates around r equals 0 with a positive effective mass. So it's stable, right? This region over here. So just to remind you that argument, the standard argument about stability requires that we have a perturbation around GR, and that's what we do not have here in the first branch. That's what we have in the third branch. Remember that this is almost a straight line, so the criteria agree in this region over here, but not anywhere else. That's just what I told you. I'm keeping ahead of myself. Okay, so this initial instability is temporary, which is a good thing. We want the system to leave the theta, so inflation can end, right? By the standard, the lower conditions just don't hold anymore, and inflation ends. And the branches are separated by a change of sign of f double prime, as I showed you. Okay, so let's go back to this dynamical character of the potential, right? As I said, what we have is the first derivative. We can integrate that, and we can have v as a function of t, right? So remember, that's what we have, right? So the red one is the numerical solution, and the dotted line is a fit that we made. What fit? So it looks like the system is going to the right, because there should be a minimum over here. But then, as time goes by, the minimum looks to be shift to the left-hand side, and then time goes by, and then we have a minimum, local minimum, a global minimum over here, where the system stays, right? So it looks like we have a minimum that's changing places. So what we did was to fit that expression over here, the numerical expression, of course, with this potential over here, right? So we have a fourth order polynomial with, actually, the c should be a function of time as well, with time changing coefficients, right? And then that's what we got. In the first branch, we have, actually cannot see, but there's actually, the second derivative here is negative. Sorry, it's positive, but the mass is not. And then as time goes by, there's this minimum over here, where the system was coming to here, and then to the left. And then after during the third branch, we have only one minimum over here, and the system oscillates around here. Right? So the black dot is just the position, the value of r at the time that this picture was taken, so to speak. Okay. So let me just open a huge parenthesis over here to talk to something that it doesn't seem related to that, but actually it is. So I think you're all familiar with van der Waals gas, right? A non-ideal gas. We have to introduce this correction of the pressure, correction for the effective volume as well. So when alpha and beta goes to 0, we do have the standard ideal gas, right? And R here, of course, is the universal gas constant. So I put a sub-index G, so we not confuse it with Ricci scalar, because that's actually nothing to do with that. But then, if we define the critical values of the pressure, the volume, and the temperature, and define these tilde variables over here as the corresponding one over the critical value, right? So tilde P is P over PC, and V over PC, and T over TC. So these are dimensionless variables. So get rid of the constants. Everything here is dimensionless. And now we define just to make a shift of the origin of the coordinates. Then we end up, this equation over here is written as this one, right? So this is going to be the description. So X is just the density shift, right? T is the pressure, is the temperature shift, and P is the pressure shift in dimensionless variables. Okay. So let me just remind you that this equation describes the equilibrium states of the system, right? Could be unstable equilibrium, We all know about supercooled gas and superheated gas. That's all is all about. But so this is, if this is the equilibrium state, right? Then can think that it actually comes from the derivation of an effective potential, which turns out to be x to the fourth over 4 plus x squared plus x plus a constant, right? Which is actually what we had if t, well, if this is u, this is v, a constant doesn't show up here because that's the derivative of this, right? And x should be the derivative scalar, right? Small x. So we can invert this relation between u, v, and t and p to write the effective temperature and the effective pressure as a function of u and v. So now the expression that we had, the fit that we had, now we can map onto this van der Waals gas with an effective temperature, pressure, and density shifted. Right? So that's going back to that shifting to dimensionless variables, right? So now it's volume, not density. That's why it's 1 over r plus 1. And then we can plot what happens to these three functions over here, right? So you probably have already seen this plot, right? This is pressure as a function of volume, as a function of temperature here. So these curves are constant temperature curves, right? So for high temperatures, remember there's a slight bending over here. So for higher temperatures, you have the standard P equals 1 over V, right? But for smaller temperatures, you start to see these curves over here that are characteristic of the van der Waals gas. And so we have this Maxwell construction over here that says, okay, so for this pressure and volume, we have different three solutions of the equations, right, of equilibrium solutions. But from here down, it's supercooled or superheated. So we have to use that Maxwell construction to define what is actually followed by the gas, right? I hope you all remember that from physics 101 or 102 or something, right? So what happens to our system when we plot, right? Because remember that now we have effective temperature, pressure, and volume as a function of r, u, and v, but u and v are functions of time that we do know. So I'd like to see what's the trajectory of our system in that space, t, p, and v tilde, okay? So that's what we got. So it cannot actually see, I couldn't find a better viewpoint for that, I'm sorry. So this is, again, pressure, volume, and temperature, the very same surface, right? And this is the trajectory. And it's almost transparent to show that it's almost on the surface, right? So it follows this path over here. There are some divergences that we have to deal with. But most of the plot, you can see that it comes brighter and fading a bit just because it's over the surface, and the surface is not totally transparent, neither opaque. So we can see it's on the surface, exactly. Okay. So we have some approximations I have to deal with because this branch over here is somewhat displaced from the surface, but I think it's a problem with the feeding that we do that's currently being done, right? And so there is another piece of information I like to give you. It's that standard textbook material, but it's not actually use it. So if we go back to standard van der Waals expression, so this is T, P, and density, 1 over V. If I plot that surface in this space, 1 over V, it makes the whole difference because now we can see here there is one region of space that we have 3 possible densities, right? Here, here, and here. And if I change the pressure, then that is no longer true. I have only smooth behavior, just like for the ideal gas behavior, and this is the non-ideal region of space. This space, right? So if I look at this picture from up, then I would see that in this region over here, I have 3 solutions, and there is a change of character because I have just like a standard phase transition. I have one local minimum that becomes the global minimum, and the system goes from one local to the other local minimum, and then it changes phases using this. So this is catastrophe theory that was developed for van der Waals gas in this book here by Poston and Stewart. And then we can work using catastrophe theory to describe what happens in this region over here. So it turns out that this is a cusp catastrophe, and this system follows almost on the border of this region over here. I think I have, yes. So the system follows the border of this region over here for most of the time. So as I said, I have to deal with some divergences in the variables. As I showed you in the previous, one of the previous plots, I told you that there's a divergence of the masses that I have to deal with. So we did deal with that, not in the catastrophe approach, but we did that. Well, actually, we did that in catastrophe approach using some deformations of this space just to make the infinity come to finite values, and you can see more details about it on Cesar's poster, which is just outside. Just to wrap it up, this is not a new inflationary model. I'm not claiming that, oh, we have a phi field in the Einstein frame, and then we have inflation. There's no matter whatsoever here. This is not another inflation approach, another mechanism for inflation, but rather it's a framework. I hope this can shed some light into what happens between Jordan and Einstein frame, and hopefully it will give some new window to what happens in different F's of R's that do not comply to those three constraints that I told you about. Another message to take home is that even if R is a linear function of the Ricci scalar, the outcome could be very different from GR. Just because in the case I just presented, the coefficient is not 1, it's really 10 times, 1 million times smaller than that. So it could be really different from GR, although it's linear. And if that's the case, those criteria, as I just mentioned, they just do not hold. Another take-home message is that just because there is no matter whatsoever in my model or any other model, that doesn't mean that the Ricci scalar should be 0, because there is not, there's no algebraic relation between the two of them, right? There's a standard differential equation for R, and it just happens that rho is the source of this equation. So it could be, yes, that R is large when the source is large, but that's not the only possibility, right? So we usually take for granted that R should be large in the early universe, but that's just because you are educated, you erase it using GR, where that's true, but that's not GR, that's F of R. So that's not necessarily true, right? Rho and R do not go necessarily together, right? And I think that's it. Thank you. Sure. This one?
So you have red with different versions of red. There's soft red and solid red. Is that?
No, actually, all of them are red, just because the surface is not opaque. So you can see this one is behind the surface.
Oh.
Okay, but this just, you can see this is a straight line, probably because the interpolation is just going from a divergent point to another divergent point. So it should be here. So that's what we're working right now.
More question?
The same thing happens here. It's all red.
A question? Yes? No. Okay, thank you again. Who is the selection? Okay.
Esse aqui?
5 or 10 minutes. I make you some 10 minutes. Can you hear me? Which one? Thank you. Can I start? Good morning, everyone. First of all, I would like to thank the organizers and Mario for inviting me to come here. It's my second time in CBPF, but the first time I give a talk here. So I'm gonna talk to you a little bit about analog models of gravity. There's nothing about cosmology here, but I hope you find it interesting anyway. So this is a picture of the experiment we did. These are my collaborators. Silke Weinferdner is the leading, like the driving force in the group, and she's the one behind everything. This is the experiments take place in Nottingham, the UK, and I visit them regularly to do this. So mainly talking, my main interests are basically two. So I want to try to see two effects that happen for black holes also in Earth laboratory, in an Earth-based laboratory, and one of them's I'll come back again to this. I'll come back again to these plots later to explain them better, but just for you to have a glimpse of it first. The first effect I want to focus on is superradiance. So superradiance is a special kind of scattering process in which you can amplify the waves you send in. It happens when you have, for instance, rotation. So here I'm focusing on rotational superradiance. And these plots are basically giving you the reflection coefficient. So basically the ratio of the amplitudes of the reflected wave by the incident wave as a function of the frequency. And you can see here if the frequency is negative, which means that the wave is counter-rotating compared to the scatterer, you always get a reflection coefficient which is smaller than 1. On the other hand, if your wave is co-rotating with your scatterer, then you may have reflection coefficients which are greater than 1. And this corresponds to an amplification. The amplitude of the reflected wave is greater than the amplitude of the ingoing wave. But you can also see here that if you go to very high frequencies, even when the modes are co-rotating, the reflection coefficient goes below 1 again. So you really need to be in co-rotating with the scatterer, but your frequency cannot be as large as you want. It has to be sufficiently small. And here is just like this same plot, but focused around the superradiant part where you have amplification. So this is all amplified. The other effect I want to focus on, I'm just gonna briefly talk about this in the end because this is a work in progress, but we believe we have interesting results. Is about quasi-normal modes. So normal modes and quasi-normal modes are pretty general phenomena. So for instance, if you have a string and you fix the endpoints, then you can produce characteristic modes on this string. If you fit like half wavelengths on the whole length of the string, you get the normal modes. But if you have dissipation in the system, then these modes will die as time passes. So they will damp out. And basically you can characterize this by two quantities. One is the characteristic frequency, the oscillation frequency, and the other one is the imaginary part of the frequency, which tells you how much you're, or how fast you're damping your wave as time goes by. So I want to try to find these two, to see, observe these two different phenomena in the laboratory, and they happen for black holes as well. So I want to try to produce them in the laboratory. Just to give you a more general idea of what superradiance is, as I said, it's a special kind of scattering process. It was originally discovered by Zeldovich, the same one from Cosmology, I believe, in 1971. And he studied the scattering of electromagnetic waves around a rotating cylinder that can dissipate energy. And if you send a wave in and then it reflects back, and the amplitude of the reflected wave can be larger than the amplitude of the incident wave, as long as the frequency of the wave satisfies this condition. Here, omega is the angular velocity of the cylinder, and m is the azimuthal number of the wave. So if you do your polar spherical decomposition, here's cylindrical coordinates, so you get your azimuthal number m, and you need this condition to be satisfied. So omega has to be positive, co-rotating, and it has to be sufficiently small for you to get superradiance. When he did this work, when Zeldovich did this work, he mentioned that a similar situation can apparently arise also when considering a rotating body in the state of gravitational relativistic collapse. So he was predicting that you could have the same kind of thing in black holes. And then other people, Misner and like works of Penrose and other people have really shown this in more detail. Starobinsky as well, and other people. So for black holes, you get basically the same behavior: an incident wave, reflected wave, a transmitted wave. And if you work out the equations, it's basically, in the end, a 1D tunneling problem like you do in quantum mechanics when you calculate the transmission and reflection coefficients over a potential barrier. Then you get this, in the end, you get a conservation relation, which is basically tells you that total energy is conserved, and you can relate this in terms of the reflection and the transmission coefficient. And you can see here that if this term inside the parentheses is negative, then you get a positive overall sign here on the right side, on the right-hand side, and then you get 1 plus something, which will be greater than 1. So that's when you get superradiance. So this basically is the same condition. Will give you this condition we had before. The same for the cylindrical, for the electromagnetic wave case. Can we expect to see this in real life? So this only happens for bosonic fields, not for fermionic fields. We have a few problems for black holes. The first one is that we can't have as much angular momentum as we want for a given mass. There's a limit to this. Otherwise, your space-time is not a space-time of a black hole. It is a naked singularity. Some other problems are that for scalar waves, even if you could find them easily, do experiments with them, the amplification coefficient would be very small. For electromagnetic waves, it's a bit bigger. Maybe you could see this, but then you have also to filter this out from all other phenomena that is happening. And for gravitational waves, which we're starting to see now with LIGO and the future detectors, maybe the amplification is much larger, and maybe we can see some effects due to gravitational to superradiance. There are some works by João who proposed some ideas to do this. There's also a mechanism that may explain how you produce. There's a way to relate superradiance and some fundamental process in particle physics. For example, how to create axion clouds around black holes and things like that. But I'm not a specialist on this. If you want to use the cylinder itself and electromagnetic waves, then the problem is that you need the rotation speed of the cylinder to be very fast. And so the velocity has to be compared to the velocity, the speed of light, and this might be a problem. Oops, sorry, it's mine. Yes, let's move on. So what I'm interested in is to observe this phenomena in laboratory, as I said before. And we have an alternative. Then instead of using real black holes, we can use analog models of gravity. So I'll spend a few slides here explaining to you what this is for those of you who don't know. The short answer is that analog models are systems that can mimic curved space-time effects like superradiance and Hawking radiation and quasi-normal modes. So they lead naturally to the question, can we see black hole evaporation and black hole superradiance in the laboratory? They were first proposed by Unruh in '81, and then but Moncrief had already used similar ideas before in a slightly different context. And in 1993, unaware of Unruh's paper, Matt Visser rediscovered the analogy, and he included angular momentum, which is necessary for us to see superradiance. So this is Unruh's original paper, and he was really, he really made that question, experimental black hole evaporation, with a question mark. And I think someone mentioned here that usually when you have a question in your title, the answer is no. And indeed, as Unruh himself says, he had to fight with the referees and the editors to have the question mark in the title, because they were arguing exactly that the answer is always no when you have something like that. But in the end, he managed to get it published, and he genuinely didn't know the answer. It was a genuine question, as he always says. And apparently, maybe, I don't know. You can tell me later in the end, but okay. Yeah, I mean, maybe I should. It's the analog of a black hole. It's not a really black hole, yeah. So this is the typical the explanation that Unruh himself gives. So I'm using the same picture and the same explanation he always does, which is very pedagogical, I think. So if you can imagine a river flowing down, and you can imagine you have a waterfall, so that the water flow is slow up here and much faster down. And you can imagine there are fish living on this river, and they can communicate with each other. So that's why they have this big ears here. And they produce sound waves, so that's how they communicate. So so sound waves have their own velocities, and if you think about classical physics here, the sound waves are going to be dragged by the flow. So suppose the flow is going down, and this fish here is trying to communicate with the other one, and vice versa. So this fish, when he produces a sound wave, the sound wave is going to be we're going to gain speed because of the flow, and it's going to reach this fish easily. On the other hand, if this fish is trying to communicate with this other one, he won't be able to do this because he won't be able to do this if the flow is too fast. So if the flow speed is larger than the speed of the sound, then the waves are not going to be able to propagate upstream, and there's going to be a point where their velocities exactly match, where the sound wave is equal to the flow speed, and that's the analog of a black hole horizon. So this is not a real black hole, and this could be just a pictorial analogy. This could not make any mathematical sense at all, but Unru later showed when he was teaching a fluid mechanics course that this is indeed a very good mathematical analogy, in the sense that if you study water waves propagating on a fluid flow, they satisfy the same equation that scalar waves satisfy around a curved space-time. And then, so if you set the flow accordingly, and you also need to make several assumptions about the flow, then you can mimic a black hole. So it's not a real black hole, but it's the analog of a black hole. For now it's classical, but there are some models where you really have quantum fields in there. But here I'm just thinking about the Klein-Gordon equation for a scalar field in a curved background. Yes, in a curved spacetime. Yeah, that's what I mean. I think he has one. I think it's the first presentations he did. He used a transparency, so he did it by hand, and he uses this transparency. But then at some point he published this and he had this better drawing, I would say, than the other one. Yeah, that's the best one. But it captures the essential features. That's the important part. And as the story goes, he realized this when he was teaching a fluid mechanics course. He came up with this analogy. His advisor was the person who coined the term black hole, and then when he was giving a lecture to people, Unru himself came up with this analogy to explain what a black hole was to a broad audience, as I'm saying here. But then when he was teaching a fluid mechanics course in 1980, I think, or 1979, he realized that this was not only a nice pictorial analogy, but also a mathematical analogy, as I explained in terms of the wave equation. I should say, since he mentioned that this might be misleading, that you don't get Einstein's equations here. So here you have the Navier-Stokes equations, or Euler's equation, if you wish, since you have to make some simplifications. But what is really analog to the black hole case is the propagation of perturbations, not the dynamical equations for the background itself. And I also have to mention that the first conference, as far as I know, about analog models happened here, organized by Mario, and that's from where I learned. I mean, I wasn't here, but they later published a book on this conference proceedings and so on, and I've learned a lot of things I know now using this book and the talks and papers that resulted from this conference. And I want just to mention that when after the conference, Matt Visser wrote, I think I took this from his webpage, so he wrote, the most promising systems for experimentally mimicking event horizons seem to be based on slow light in BSC systems, Bose-Einstein condensates, with resonance-induced transparency, quasi-particle in superfluids and acoustic oscillations of the phase of the condensate fields in BECs. Considerable enthusiasm and hope was expressed that one or more of these analog systems might be brought to laboratory fruition in the near 5 to 10 year future. And as Mario and the editors of the book, Mike Visser and Grigory Volovic, mentioned in the book, though this is a book written by theorists, we strongly want to encourage experimental participation in these ideas. Not all of these approaches will necessarily pan out in feasible laboratory experiments, but we feel that there is already enough known to strongly suggest that it's only a matter of time before a laboratory scale analog black hole is actually built. The sooner the better, and experimental feedback on these subtle issues will be extremely useful. And in fact, it took less than 10 years. Here's a science paper where some people from the UK published their findings on having the event horizon in a fiber optical system. Later, these are just two examples. There are more systems like this. Here there's an example of a BEC condensate from 2010, a PRL, where they also showed that they obtained the analog of a black hole horizon in the laboratory using Bose-Einstein condensates. So what about Hawking radiation? So these are two realizations of analog event horizons in the laboratory, fiber optics and BECs, but what about the analog of Hawking radiation, the analog of superradiance? So we're not going to go into the details here about Hawking radiation, but I just want to mention that there have been some work on this, and recently, from 2006, Jeff Steinhauer from Israel claimed to have found really quantum Hawking radiation in a BEC-like system. There's still some debate about these results, and people want to study and have to study this more carefully, but there's been some very interesting work on this. So the system which I want to focus is water, so the simplest thing you can think about for these analog models. But instead of using sound waves, as in the pictorial analogy I gave you, I want to use surface waves. So surface waves, they propagate on the surface water, and instead of being pressure perturbations as in the case of sound waves, they are and then instead of propagating inside the fluid, they propagate just on the surface. The only restoring force here is gravity. So they are sometimes called gravity waves, not to be confused with gravitational waves, two different things. And people have studied these surface waves for more than a century in fluid dynamics, and they actually have they've known this kind of analog black holes for a long time, even though they don't refer to them as this. So they have like they call the event horizon a blocking region, and they have a parameter to estimate if the flow of the water is faster or slower than the flow of the speed of the waves, which is called the Fraud number. But they never studied it in the context of black holes and really that only started when Roux published his work. So why I want to use surface waves instead of sound waves? So they're basically, the main reason is that surface waves have much slower speeds. So their speed is given basically by the square root of g times h, where g is the gravitational acceleration and h is the depth of the fluid. So if g is 10 meters per second square and h is 10 centimeters, you get square root of 1, which is 1 meter per second. And this compared to the speed of water, speed of sound in water, which is 3 orders of magnitude higher, makes it much easier to set up a flow where you can achieve the same speed as the wave has. So here I'm going to talk about some of the experiments I've been involved with. I've always been a theorist, and I've always studied only theory, but this was really something that motivated me, and I was really happy to be involved in these experiments. So it started in 2010 when I was visiting Sigaud in Italy. We had studied it in theoretically, and we wanted to see if we could maybe have a chance to do an experiment. So we went to a store, bought a large bucket, borrowed a slide projector, like those wood ones, borrowed a camera, simple digital camera, and mounted the frame in the bathroom of a laboratory, of one of the laboratory buildings in ICTP in Trieste. And we just wanted to get a feeling of what would it be and how much work it would be. And later, Sigaud got some grants to build a real experiment, and here are some pictures of the current setup, or a very recent picture of the setup. I'm going to explain to you in a bit what these things here are, but basically you can see here a water vortex, and here's the detector which we use to see to measure the flow and the surface of the flow. But I'm going to get into details very soon. So just to remind you, as I explained in the first slide, we want to see superradiance. So we want to see if we can get reflected waves, so scattered waves, which have higher amplitudes compared to the incident waves. And for this to happen, we need co-rotating waves, and they need to have sufficiently slow frequencies. So in this plot, you need to focus on this part of the plot here, so you get this. Different curves are for different background velocities, for different flows. And this is focusing on the m=1 case. So the first one, you do your polar decomposition, the first mode, which is the one which you can amplify better. Sorry, can you say that again? If you never get what?
Counter-rotating waves,
right.
But near zero. Because then
right.
you never get amplified.
Yeah, amplified, you mean? Yeah, they can never get amplified. Only co-rotating. Yeah, these curves here go to 0 when omega is 0. They go to r=1 when omega is 0. You can see here that when omega is 0, they are all going through 1. Let's move on. So here's some more pictures of the setup. Here's a picture from the side where you can see the vortex. Here's overall general picture of the setup. We have water flowing on this tank. There's a drain in here. Water is coming in from an inlet, which is here on this side. So water comes in from the side. It has an angular momentum, and it is, since it's flowing in a direction that's not going directly through the hole, so it swirls down the hole and drains like a bathtub you have in your home. There's a tank beneath this one which captures the water that's draining, and there's a water pump that takes this water from the bottom tank and flows it back in the system. On this side here, you can barely see, but here's the wave generator. So it's basically, it's it's much improved now, but when we did this experiment, it was just a metal plate going up and down the surface. And you can't see here, but on the ceiling, we have the detection equipment, cameras, and our detectors, and some computers to do the analysis. The water is green because we use some dye, and this dye makes it easier for the camera to see the surface, so that we can really only see the surface and not the bottom or other parts of the flow. So we really want to focus on the surface, and that's why you use this green dye here, which is called we use a substance called fluorescein to get this. The water tank is basically 1.5 to 3 meter wide. So it's a closed system. As I said, water is pumped from an auxiliary tank, which is beneath it. So we produce waves here. They propagate towards the drain. They get scared. They get not scared. They get scattered, and then we observe them, and we want to see if they are amplified after the scattering or not. Here's another picture, a schematic picture. So here the analog of the black hole is near the hole, where since the fluid is accelerating towards the hole, when you get sufficiently close to the drain, you get very fast rate of velocities, and this rate of velocities can be larger than the wave speed. So water inlet, water comes in from here, swirls down the hole, and then goes to the auxiliary tank at the bottom. Picture from the side so that you can see the detectors here on top. And here's a picture where you can see the waves propagating on the surface and the vortex there. And what the detector is doing is it's measuring the height of the flow as a function of time. So in each time step, it gives us, as a function of coordinates x and y on the surface, what is the depth of the flow. And since we have this for several time steps, we can really understand what's going on the surface. We can understand the waves that are propagating in there. This is the detector, and this is a sample image that it produces. So the surface at a given time step. Just want to mention that this was a joint invention between Silke's group and a company in Germany. There's a patent application that came out of this. Here's just for you to have an idea. We also measure the flow using a technique called particle image velocimetry. So we shine a laser on the surface of the water, and we have some very small particles, fine particles in there. And then by tracking the particles, we can basically measure the flow. And I'm not going to focus much on this, but this is basically the angular velocity and the rate of velocity. You can see that here, really near the center, you have a very huge uncertainty, and that's because that's exactly where the free surface of the flow is bending down. So we get huge uncertainties in here. Basically, the flow is getting almost vertical, so the waves, we can't see them anymore. So we believe we have the analog of an event horizon here for these flows and these angular velocities, and for this depth. But we cannot be completely sure about it. So as I'm going to say later, the phenomena we see could be caused by two different mechanisms. One is this typical black hole superradiance, where your modes get trapped inside the black hole. And the other one is like in Zeldovich cylinder, where instead of an event horizon, you have dissipation, and then that's how you get your modes away from the system. So maybe here we could have vorticity inside the core playing an important role for us to get superradiance. Maybe it's because of an analog event horizon. Maybe it's not, so we're not sure, but maybe it's a combination of both things. And this is one of our next ideas, is to improve this and make sure to make sure what kind of mechanism we have here to produce superradiance. And this plot here is just showing to us that the flow is really, to a good extent, axisymmetric, which is one of the assumptions we have for superradiance. Otherwise, if it's not axisymmetric, you can mix different M modes, different azimuthal numbers. For example, M equal 1, you can mix into, with M equal 1, you can produce M equal 2 or M equal 3 and so on. And then it's a much harder work to analyze if you have superradiance or not. So here's a typical picture that we get from the sensor after we treat the data. So we have a plane wave created on this side where the wave generator is. It's propagating towards the drain, and it's being scattered. So that's why you see all this interference pattern here, which is basically the incident wave plus the scattered one. You can see an interesting effect here, which is the analog of the Aharonov-Bohm effect, which it basically is telling you that in these terms here, in this system, it's basically telling you that since the vortex is flowing this way, down here below the drain, your wave is going from left to right, and the flow is also going from left to right. So that's why you see less wave fronts than on top, because here the waves are going against the flow, and then that's why you see more wave fronts. And you can actually quantify this difference by measuring the flow velocity. And this was work done in the 80s, I think, by Michael Berry when he studied this effect for surface waves. So how do we do our data analysis? So as I said, we have our height field, which is basically the signal, is a function of the position x and y on the surface, and as a function of time. So we have the depth of the fluid as a function of position and time. So we do a Fourier transform in time and in position. So first we Fourier transform in time, and we filter out the excitation frequency. So we know what frequency the wave generator is producing because we set it in there. So 3 Hertz, for instance. So we know that the waves will have 3 Hertz. So we filter our signal around 3 Hertz. We have some higher harmonics, so twice and 3 times the frequency, but they are small, and we worry that we had the care we were careful to make them small, and we also filter the background flow, which is very zero frequency signal. So we work here in the frequency in the range 3 Hertz to 4 Hertz, more or less. So after we do the Fourier transform and filter out the frequency, we decompose our signal into azimuthal waves, as I said before. So we make this azimuthal decomposition. So our function, which has now been, there's no more time dependence now, only frequency dependence, since we did our Fourier transform. Now we do our angular transform so that we can get rid of the angle as well, and then we decompose our function. This is basically telling you what the surface is doing. So it depends on the azimuthal number m, and I should also have here the frequency. But we filter all the frequencies. So then for each azimuthal number, let's say m equal 1 or m equal 2, we do a Fourier transform in space. So basically, in simple terms, what we are doing is we are separating the waves as an ingoing part and an outgoing part, and k is the wave number of the waves. And these are the amplitudes of the incident and of the reflected part. AM is the incident part, and A out is the reflected part. And by comparing these amplitudes, we were able to see superradiance. We were able to see an amplification. It's a small amplification. Here it's a very conservative result. Maybe it's better than this. I'll explain it to you in a bit. And the error bars are also big, I know, but this was the first time it was seen in the laboratory, and we plan to improve it in future experiments. So here, for you to understand it better, how we get this amplification. So we have different M modes, -2, -1, 0, 1, and 2. Basically, we can see higher M modes like -3 or +3 because, or even higher because the limitations of our tank are the size limitations of our tank. So here is the Fourier transform in space, and you can see here the amplitude on the y-axis, and on the x-axis is the k number. So positive k and negative k, one corresponds to the ingoing wave and the other one is the reflected wave. So negative k is the ingoing wave, positive k, so the yellow part here is the reflected wave. And you can see that for negative m's, the amplitude of the ingoing wave is much bigger than the amplitude of the reflected part. But the reflected part is increasing as you go to positive m, and then at m equals 1 and m equals 2, we can see an amplification. Here's just the signal in space, not in Fourier space, in usual position space. And the points are the experimental data, and the curves are the fits, which, if you use this very simple function here, so basically assuming that these are delta functions around the frequencies. But in real life, they're not delta functions. There's a spread around the frequency, and so when calculating the ratio of the amplitudes, we can actually, we do it two ways. We also integrate, do some kind of integration here to consider also the spread of the peaks. So we can see here that for m equal 1 and m equal 2, we see amplification, and for -1, -2, and 0, we don't see. So basically, these are the counter-rotating modes, and these are the co-rotating modes. Here's a plot of the spectrum we get. As a function of frequency, the reflection coefficient, the stars here, which is this curve I'm following, we get when we cover the drain, so there's no drain anymore. So in this case, we don't expect any reflection, any transmission, any dissipation, everything should be reflected, everything that goes in should come out again. And so this curve here, instead of going down, it should be a straight line around 1, but we don't see this, and we have some explanations for that. It's possible, probably because we have some sort of dissipation because of the dust on the surface of our system, that as we increase the frequency, we get more dissipation. So this is the baseline, which if you are very confident about the results, which you should use to see if you get superradiance or not. So anything that is above this line gives you superradiance. So for instance, m equal 2 and m equal 1 are this the yellow and this pink curve here, which are above the purple curve for a certain frequency range. When I mentioned the numbers 14 plus or minus 8%, we were getting the peak and divided by 1, assuming that this line was at 1. But if you consider that you have this dissipation, then the amplification is even bigger. So we may be able to claim that the numbers are bigger than this. But just a second. But we want in the future also to be more careful about this dissipation and make sure that we get this line at exactly 1. It's
difficult to understand why the last yellow triangle is so much lower than the other one.
So typically you only get superradiance for a certain range of frequencies, right? So they go big. Probably, yeah, probably yes. Oops, wrong way. This curve here is this one. So they go up and then they go down again. So if the frequencies, yeah, so probably we're going down already. But so this isn't my final conclusions, but I can say now one of the things we want to improve is to have a more detailed quantitative result. We want to compare this with theoretical predictions and make sure everything is consistent with what we expect from theory. But this is not a simple task to do. Here's a similar plot, but instead of having the frequency on the bottom, on the x-axis, I have the m numbers, the azimuthal numbers, and the reflection coefficient on the y-axis again. So we can see without the vortex, we have a reflection coefficient around 0.8. So this is for a fixed frequency, so I'm not changing the frequency anymore. So for this fixed frequency, reflection coefficient around 0.8 when there's no vortex. So the water is standing still. As I said, ideally, we would like this line to be here on 1, since when there's no vortex, everything that goes in goes back again. But because of this source of dissipation, which we believe is due to dust on the surface, we get this below 1. And here is the reflection coefficient when we have the vortex, the asterisks, and we can see they're considerably larger, above 1 if you're conservative, and above 0.8 if you are willing to trust, to be more flexible, I would say. So just some important details here. So negative M modes, so basically the counter-rotating modes are always absorbed. So they are always absorbed, always these ones, always below the baseline. M equal 1 and M equal 2 are amplified. The amplification we got here was bigger for M equal 2. So here, if you measure where this point is, it's around 1.14. That's why I say 14%. But as I said, comparing to 0.8, should be even bigger. And that's basically the main result we got, and we want now, as I said, to make a comparison with theoretical data. But there are several problems, and the thing is that in real life, we have vorticity, we have dissipation, viscosity in the system. We have to take into account that the dispersion is not linear anymore, and the basic analogy assumes all that. Linear dispersion, no vorticity, and no viscosity. So it's a really tough question to include them. I'm almost finishing already since I started. I know, but I think I started early, yeah. But I can spend maybe 5 minutes here talking about the ring down. So what we are trying to do now, this is work in progress, is to see the normal oscillations of the system, of a vortex. So if you think about black holes, basically the main idea behind black hole spectroscopy is that a black hole has a very particular spectrum of their natural oscillation frequencies, and by identifying this spectrum, in principle, you can identify the black hole. By measuring this spectrum, you can identify the black hole. So if you can, for instance, using LIGO or future detectors, so this is something people are already starting to do with real data. If you can measure the ring down of a black hole, so as it's oscillating down after a black hole merger, for instance, when the merged black hole is relaxing to a final state, it will produce gravitational waves. So by measuring the decay in time of these gravitational waves and the oscillation frequency, you can get a spectrum. And then from this spectrum, you can basically identify the mass and the angular momentum of the black hole. So in some sense, it's a very simple, black holes are very simple in the sense because there are no, if we believe the no-hair conjectures, they only depend on mass, angular momentum, and charge in standard GR 4 dimensions. Since charge there's a tendency for charge to be eliminated in astrophysical scenarios, so we basically just hope to see angular momentum, significant angular momentum and mass. So basically by identifying this natural oscillation modes of a black hole, we can tell what the mass and the angular momentum are. Sure. Right, but you have to assume some. Yeah, you have to assume some Matter conditions and so on, and but I agree, it's a theorem. Yes. Right, I agree. Not disagreeing with you. And what I was saying. So we can identify the mass and the angular momentum of a black hole by looking at the quasi-normal modes. In very simple terms, this is what you do when you, I mean, not what you do, but you can think of the quasi-normal modes as the ringing of a bell. That's a classical example. When you ring a bell, you hear the sound and it will dissipate in time exponentially. And that's basically what you're trying to measure for a black hole. So here is some plots for these analog black holes where we see the oscillation frequency as a function of the rotation speed of the black hole, of the analog black hole, of the vortex. And here the same thing, but instead of the real frequency, you have the imaginary frequency. So what you're seeing here is how fast the modes decay in time. And basically, this is the one which decays slower, and these are decaying faster and faster as you go down. There's a discrete set of modes. That's why you only have a few lines in these plots. And we hope to see the same thing in the laboratory. And I have some initial results. So basically what we're doing here is we are not sending any waves toward the system as we did in the superradiance experiment. What you're doing is we're just looking at the noise of the system, and we're trying to filter out the characteristic, the frequency of this noise. And the procedure is similar. to the one we do in superradiance. We do Fourier transforms, do polar decompositions to find azimuthal numbers, and this is our experimental data with error bars. So we picked several. I think this is for like 29 experiments. The depth of the fluid is 5 or 6 centimeters. And this is the relation we get between m and the frequency of the wave. So here, these are the counter-rotating modes. We have 2 branches for co-rotating modes. We're still trying to understand this. We want to make sure these are really the quasi-normal modes and not simply the dispersion relation of the fluid that we are seeing. And we have some theory model for this. And here's basically, if you get this, the points here without the error bars, oops, you put them in here. I'm just using the negative ones now. We're still trying to understand the positive ones because the predictions are not so good for them. And here's a feed with 2 parameters which are basically telling us what is the background velocity. We don't think this is because of a black hole, so I have to be honest with you. We don't think this is due to a black hole. This is just a vortex, natural oscillation of a vortex. But the next step would be to really make sure we have the analog of an event horizon and try to really see the ring down. Here we don't see the ring down, we only see the real part of the frequency because we are constantly exciting the system, so they cannot decay in time. As soon as one mode starts decaying in time, we're producing another one, so they cannot decay because we're constantly exciting the system. We are maintaining the background fixed by having this flow that is fixed by the pump. So this is, as I said, work in progress, and we hope to have some better conclusions and better explanations soon. So as I said, next steps are, I didn't say this, but so far, since the beginning of analog models, most analysis and experiments were done in 1D systems, but we want to explore more possibilities in 2D systems where you can have more degrees of freedom, like in superradiance where you need rotation. As I said, we want to match numerical predictions with theory for superradiance. Another thing we want to try to do, as people have done this in 1D systems, or in classical systems, so it's not really quantum Hawking radiation, it's a classical analog. So we have to take this with a grain of salt, but we want to see Hawking radiation and superradiance by measuring noise correlations in the system. And this is about the last thing I was telling you. We want to match the ring down spectrum with some theoretical one with experimental observations. And I just want to finish by saying that I know when people in analog gravity always get a hard time because people say this is not real gravity, it's a different system, and I know, and I completely agree with it. The original motivation, well, 10 years after João published his paper, ideas from analog gravity were used to try to explain the Transplanckian problem in gravity. So in some sense, we expect this to give new ideas to gravity, even though they are very different systems. Maybe here, by trying to see this ring down spectrum, we can give new ideas to LIGO people and so on. But even if you don't like this part about analog models, even if you don't think it tells us anything about gravity, it tells us a lot about other physical systems. And for that reason, by itself, I'm very happy to study this, even if it's not telling us anything about gravity. So we are learning a lot about fluid dynamics, Bose-Einstein and condensates, and other systems by doing this. Thank you very much. No, and I don't know if people have tried something. I maybe have read something, but I don't know. We didn't do anything. The question is that soliton are known this. They are right, but yeah, but solitons you need like a special condition for the dispersion relation, right? If I recall correctly, like you need to match the dispersion with. Yeah, I mean I don't know. Might be interesting.
So you mentioned that the superradiance that you detected was, you're not sure if it was from an analog black hole or from some dissipation.
Yeah.
What do you plan to do to be sure that it's for some analog black hole?
So I think the most important thing is to really get to measure this with more accuracy. So this is the radial velocity as a function of the radius. And this is telling you, this is negative because the flow is going inside the hole, and you're getting faster and faster as you go inside. If you have any rotational vortex, this behaves as 1 over r. So it goes infinitely down here, and since the rate of velocity is becoming infinite, then your wave speed is going to be definitely smaller than this. So your modes are going to be trapped inside the vortex. However, in real life, we don't have any rotational vortex. We always have some rotational core, at least in our system. So this behavior here this doesn't go to infinity. There's a maximum where this stops, like this here for the angular velocity. So in theory, if it's rotational, it goes as 1 over r. But in real life, it's not so simple. So we want to really measure this more carefully, and that's the main. Sorry, how much? Oh, one thing we want to do is to measure this carefully, we need very expensive cameras. I mean, at least not expensive to usual to large scale experiments, but still like I don't know, like $50,000 for a camera, I think. So we have only one, so we can only see a sheet on the surface. But if we had another camera, and that's something Silk is trying to get right now, we could also see the vertical velocity. So then we can really have more control over the whole fluid. And we can try to, by playing with the setup, get a more controlled flow where we can make sure the needed assumptions are valid. So this is one idea. Another thing we need is a better theory that incorporates this behavior. But then when you start including vorticity and other things, then you start to lose the analogy of the black hole. So then we could still have superradiance, but it would be we would maybe lose the analogy of a black hole.
Excuse me. Maybe I'm missing some basic knowledge between the relations between superradiance and Hawking radiation. But after the first question and the conclusions, you didn't mention Hawking radiation explicitly during these talks. Can you maybe explain basically how the analogy works for Hawking radiation?
It's basically, that was the main point in Unruh's original paper. He he argued that you don't need general relativity to have Hawking radiation. You just need field in a curved space-time, like scalar field or some field in a curved space-time, and you need a black hole horizon or some kind of horizon in the sense that your perturbations and the flow in your system are, in the sense that in this curved space-time you have a black hole. And I really didn't focus on Hawking radiation here, and I didn't study it very carefully, but I know people try to do the same, and as we did for superradiance, but for Hawking radiation, and this here is the most recent and most important result. They set up an analog black hole horizon using a BC, and then they try to measure spontaneous particle production. Yeah, so there's basically, I don't remember the details, but here he uses like correlations and positive and negative frequency modes that he tries to find in the laboratory.
The laboratory is also a fair creation.
Yes.
Analysis of actually fair creation.
Yes. So this is really a quantum system. So that's really what differs, in my opinion, this from the like classical water and there are two kinds of analog systems: classical ones like water and so on, and really quantum systems like BECs. And here, the claim is that they see particle production. But I think the next step here is to really measure the thermal spectrum of the radiation, so that this they haven't done yet. In this case here, with water, there's some sort of spectrum, but again, it's all this, we have to rely much more on the analogy. Here you still have to rely on the analogy, but it's an intrinsically quantum system, so you don't have to stretch the analogy so far.
Mauricio, in both water experiments, you use the surface waves, right?
Yes.
Did they have an effective mass, right?
Sorry?
The surface waves, they have an effective mass, or it's
no, this is massless. So we have a model, which I don't have in the slides here, but when we include vorticity, we may, in some limits, treat it as a mass term. So it might behave as a mass term.
Okay, but not in the first one.
No, this is the original analogy, and what we are using here is that you mean a mass for the particle, you mean?
No, I mean for the wave equation. It's a Klein-Gordon with an effective mass.
So no mass here. It's a massless Klein-Gordon equation. Yes.
Okay, but the velocity depends on the depth of the water, but
yes,
that comes from the D'Alembert, not from an extra term.
Yes, it comes from the D'Alembert in a curved space-time. Yeah. The metric depends on the depth. Yeah.
Can you create a region in the fluid that the income waves are not allowed to enter, like just mimicking a white hole?
Yes, and the idea is here we have a drain, and instead of a drain, you need a source where water was flowing away, and people have even like played around with the possibility of mixing a black hole horizon and a white hole horizon, and then you can create some kind of a laser effect and some instabilities. And I think there's even some experimental work on this. But yes, in principle you can. And in fact, this first paper here, I helped in the really initial stage of the experiment, so I don't know all the details, but in the end, they have the analog of a white hole horizon, not a black hole horizon.
No more question? Okay, thank you again.
Thank you.
I would like an announcement, actually, mainly for students. Just remind you that you have to sign the presence paper on the paper. And at the end of the school, you might have a surprise, a gift. Okay, just to motivate you to sign.